Hello and welcome. In this video, I'm going to show you how to detect and correct for heteroskedasticity in OLS regression analysis. First of all, I would like to retrieve some file from the online, and I may use a number of different commands. There are a lot of data sets available online. I may use stata example files, or I can use any different source to retrieve some data file for training and data analysis. So one of the best way is to get some file from bcuse command, and bcuse command basically means bcuse BC stands for Boston College, and it means there are a large number of data sets that are available on the Boston College website. And if we use this command bcuse and then we give the name of the file that we know that it's there, Stata will automatically retrieve that file. So yes, you can see Stata downloaded that file from the internet and from the website of the Boston College. If bcuse is not installed on your in your Stata, so for the first time you will use this command ssc install bcuse, and after that you can say bcuse and then name of the file and then hit the enter key, and you will download the file. So my file is here. These are the various variables: wage, education, experience, tenure. This is a dummy for race or color. This is dummy for gender, and this is dummy for marital status, and so on. And finally we have some other variables in this file. For example, this LWage stands for natural log of age, and experience square is there, and finally we have tenure squared. So I would do this analysis in different forms, and I'll detect heteroskedasticity, and finally I will tell you how can we correct for heteroskedasticity. So I have a do file. Here I have already made this do file. So first of all, I will run this regression, and let me copy this command from here so that I save some time. Here is if I click enter, so this is the output of my OLS regression. After that I will test for the Bruch-Pagant test. So the command is here head test, that is heteroskedasticity test, and then after the comma we write RHS for right hand side and F state. So it will check heteroskedasticity for us for these variables, and it will give us the F state. And the F state is there, but you see the probability of this F value is highly significant. So we reject the null hypothesis that this data is homoscedastic. So the variances are heteroscedastic. So there are a number of ways to correct for heteroskedasticity. One way is to specify a different functional form. Another way is to use weighted least square, and then another way to use robust standard errors. So first I would like to try another functional form in which I will regress the natural log of wages on the same variables, and then I will use the heteroskedasticity test, and I will see if there is any improvement or not. So I'll copy this command, and only I will make only one change, and here I will write L wage, and after that this is the output for the OLS regression of natural log of wage on education, experience, and female. Now again I will use this command for the Bruch-Pagant heteroskedasticity test, and let me see what happens if I. So this time I just made one change in the OLS regression, and instead of wage, I use natural log of wage, and you see that the Bruce-Began test changed the result, and now this p-value shows that we fail to reject the null hypothesis of constant variance. So now it is homoscedastic. Now let us suppose that if it didn't work, then I will have to try a number of different functional forms. So another way of this is to use the weighted least squares, and in the weighted least squares usually we generate variables from the existing variables, and we multiply them by some weight. For example, wage underscore w is equal to 1 divided by education raised to the power 0.5 or 1 by 2. Similarly, this is another file. Let me copy all these, and I will click enter, and these variable will be created. So if some variables are already there, then it will give me a message. So it generated a new variable wage. That is, we will multiply wage, original wage, by this weight 1 divided by education square root of the education, and this is a new variable for education. This is a new variable for experience, and so on. And if we regress wage w on this variable education underscore w and experience underscore w and female underscore w and b naught underscore w, then we will get weighted least square, and then we will again run the heteroskedasticity set, and we can see whether it works or not. So let me try a number of different methods, but there is another method that instead of regressing the weighted uh, least square, I can use this command, in which rest of the thing is OLS, but finally I write this thing AW stands for analytical wage, and that is equal to 1 divided by EDUC, that is education. So if I hit enter, I get these estimates. So these are the estimates for the weighted least square, in which I have multiplied each variable, that is the dependent variable, the independent variable, and that is equal to 1 divided by education raised to the power 1 by 2. Now again I can run the HET test, comma, right hand side and F state. It doesn't work. Then I can use say for example education square. So let me copy that file from there. Instead of this I am using this, and at the same time I will run the heteroskedasticity set also, test also. So here is the Bruce-Began test, but it didn't work. Then I will use another test for tenure. This time I am using the weight 1 divided by tenure. So if I do this, this is my regression output, and I also ran the heteroskedasticity set, and it still doesn't work. So this weighted least square is basically trial and error process, and we can repeat it again and again, but it doesn't mean that we will leave it and we will throw it away. So there is another way. If you couldn't solve the problem of heteroskedasticity by using different weights, there is another method, an alternative method, and that we can use that is of robust regression, and that is I will regress the same OLS regression, but at the end of the OLS I write robust, comma, and after comma I write robust, and if I hit these are the robust errors. So these coefficients and those coefficients that we got with the OLS, these are exactly the same. So let me compare these for you. So I will store estimates for the robust, EST, ROBUST, and then I will run another regression of the OLS and store the OLS results. So this is the result of the OLS. Now if you look at these coefficients and these coefficients, these are exactly the same. Now I will give the command ESTOUT, and it gave me this table in which the coefficients of both the OLS and the robust are given. So these are exactly the same. So the robust standard errors only changes the standard errors. Rest of the things are the same. That is, their coefficients are the same. Finally, I would like Stata to give us some other information with this table, and for that I am using stout command, that is here. And now you see this command gave us these information. It added standard errors to the coefficients, and it also gave us stars with those which are significant. Now if you look at these coefficients, this is the coefficient of robust and this is the coefficient of the OLS model. These are the same. This is their standard error and this is standard error. This coefficient is also the same as this one. Similarly, this coefficient for the female which is negative is also the same, and this is the coefficient for the constant, and it is exactly the same. So the only difference between the robust and the OLS estimation is that rest of the estimates are the same, only standard error and t values changes, but the original coefficients remain the same. So ladies and gentlemen, I think it was quite helpful for you, and if you have any question regarding detecting or correcting for or fixing heteroskedasticity, you may leave a comment below this video, and I'll try my level best to come up with my answer.